In March 2023, a single sentence spoken on a stage in Texas sent shockwaves through Chinese rare earth mining stocks. By early 2026, the technology that sentence promised still didn't exist in any production vehicle. One announcement, Nikampuda 3 years, zero delivery. That gap is the most revealing thing Tesla has done in years, and almost nobody is talking about it the right way. Here's what actually happened. At Tesla's Investor Day in March 2023, the company's vice president of powertrain engineering told the room that Tesla had designed a next-generation drive unit, a permanent magnet motor that used absolutely no rare earth materials. Then he put a slide on the screen. The current motor in a Model Y uses 3 separate rare earth elements. Roughly 500 grams of the first, about 10 grams each of the other 2. The new motor would use 0 grams of all 3. Shares in Chinese rare earths mining companies dropped. One sentence, one slide, and a whole sector moved. As of early 2026, that motor has not appeared in any public filing, production disclosure, or investor material. No production date has ever been given. The motor Tesla just put in its fastest Model Y still depends on magnets that trace back to China. This is the story of the hardest engineering problem in the electric vehicle industry, and why the company most determined to solve it hasn't solved it yet. Tesla is named after the man who invented a motor that never needed a magnet. Nikola Tesla's AC induction motor generates its own magnetic field from electricity. No neodymium, no mining, no geopolitical dependency. Tesla, the company, built its first cars using exactly that kind of motor, then deliberately walked away from it. In an induction motor, the rotating part carries no magnets. The stator creates a rotating magnetic field, which induces a current in the rotor, and that induced current creates a second magnetic field that chases the first one. The rotor makes its own magnetism from electricity on demand. The original Tesla Roadster used an induction motor. So did the Model S. Then came the Model 3 in 2017, and Tesla changed course. The Model 3 introduced a permanent magnet motor. Instead of inducing magnetism in the rotor carries fixed magnets made from neodymium iron boron. The reason is efficiency, and it's not a small difference. An induction motor continuously spends part of its energy budget generating the rotor's magnetic field. A permanent magnet motor gets that magnetism for free. The magnets are already magnetic. More torque at low speed, better real-world efficiency, more range from the same battery pack. For a company trying to build an affordable long-range car, the choice made itself, and the entire industry made the same call. But here's what that choice cost. Neodymium magnets require rare earth elements, and the global supply is heavily concentrated in China. Not just in mining, but more critically in processing. Turning ore into magnet-grade material is the part China dominates. So a decision made purely on efficiency in 2017 quietly handed a strategic dependency to every automaker that copied it. Which means when Tesla announced in 2023 that it wanted a permanent magnet motor with 0 rare earths, it was trying to undo a trade it made years earlier, without giving back any of the efficiency it had bought. That is the actual engineering brief, and it is far harder than it sounds. The problem is measurable. Compare the strongest ferrite magnet high, the obvious rare earth-free alternative, against the neodymium grade used in a drive unit like the one in a Model 3. The ferrite magnet has roughly 1/9 the maximum energy product. Its resistance to demagnetization is more than 3 times lower. 1/9. That is the gap any engineer trying to delete rare earths has to close. It cannot be closed with a better factory or a smarter supplier deal. It has to be closed with physics. How do you get a weak magnet to do a strong magnet's job? There are only a handful of levers. The first is geometry. If the magnet is weaker, you need more surface area at the air gap, the narrow space between rotor and stator where almost all magnetic energy is concentrated. To use weaker magnets without making the motor bigger, you have to change the shape of the motor itself. The second lever is speed. Power is torque multiplied by rotational speed. If weaker magnets cost you torque, you can recover power by spinning faster. This is where Tesla's carbon sleeve rotor comes in. In 2021, the Model S Plaid launched with what Tesla says was the first production electric motor to use a carbon fiber sleeve wound around the rotor under high tension. The sleeve puts the copper rotor into compression, stopping it from expanding outward under radial acceleration. With that expansion contained, the rotor can spin considerably faster. A tighter air gap means a stronger effective magnetic field. And carbon fiber conducts less heat from the stator into the rotor, lowering the risk of demagnetization at high temperature. Motor design specialists have noted that retaining sleeves are a known concept. What Tesla did was make one work in mass production at automotive cost. That's a manufacturing achievement, not a physics discovery. The third lever is everything around the motor: power electronics, battery chemistry, factory footprint. There is no single trick. Weaker magnets get compensated for by shape, by speed, and by the electronics around them, all at once, which is exactly why this has taken longer than anyone expected. Now, what actually shipped in 2026? The 2026 Model Y Performance carries Tesla's newest motor hardware. Combined output 510 horsepower, up from 456, a gain of roughly 50 from the same footprint. 0 to 60 in a claimed 3.3 seconds. System torque estimated at 513 pound-feet. Here's the detail almost every write-up buried. The front motor is an induction motor. The rear motor is the permanent magnet synchronous one. That's not an accident. Induction motors are excellent at high power and lose very little when not being used, which suits a front axle that spends most of its life idle. The permanent magnet motor handles the efficient everyday work at the rear. The dual-motor Tesla in 2026 is a compromise made physical. The magnet-free technology handles the burst. The magnet-dependent technology handles the range. The battery lands in the low 80s of kilowatt-hours. EPA range came out at 306 miles, more than 10% better than the previous performance variant despite the added power. Peak charging around 250 kilowatts. Base price just under $60,000. More power, more range, lower price. That is a genuinely good result. Nobody deleted a rare earth element, which would be a fine place to end, except for what happened to the supply chain in between. In April 2025, China imposed export controls on 7 heavy rare earth elements and the magnets made from them. This wasn't a price move, it was a licensing regime. Automakers trimmed production while licenses were worked through, not because the magnets became expensive, but because they became uncertain. A drive unit missing its magnets isn't a slower car, it's a car that doesn't get built. In October 2025, China went further, introducing a rule targeting any foreign-made product containing more than a trace amount of Chinese rare earth content, at a threshold of 0.1%. That reaches far beyond magnets. Then on November 7, 2025, China suspended that expansion for 1 year as part of a broader trade truce. The controls are paused, they are not withdrawn. Every automaker now knows exactly how exposed it is, and knows the clock on that pause is finite. So the 2023 announcement stopped being an efficiency project and became something closer to insurance. Tesla was trying to remove a single point of failure that a foreign government can switch on and off. 3 years after that Investor Day slide, there is still no confirmed commercial deployment of a rare earth-free Tesla drive unit. The reason traces back to that 1/9 number. Ferrite is the obvious substitute. One ferrite-based EV motor design matched the output and rotational speed of a comparable neodymium motor. while being about 30% heavier. You remove the dependency on China, and you add roughly a third to the weight of the drive unit. In a car where every kilogram costs range, a 30% heavier motor is not a small compromise. It's the kind of compromise that loses a comparison test. The alternative works. The alternative costs you the thing you were competing on. There's a second pressure almost nobody accounted for in 2023, humanoid robotics. Every joint in a humanoid robot needs a compact, high-torque actuator, and those want the strongest magnets available if robotics scales the way its backers expect. Demand for rare earth magnets goes up at exactly the moment the industry is trying to design its way out of them. Now, the other side, because the fair version is more interesting. Tesla did not achieve nothing. At the same investor day, the company said it had already reduced rare earth content in the Model 3 powertrain by about 25% since 2017. A real shipped reduction delivered without a headline. Every dual-motor Tesla already runs one axle with no rare earths. The carbon sleeve is real, and Tesla flagged rare earth dependency as a serious risk 2 years before China turned it into a live trade instrument. Most of the industry was still treating it as a footnote. There's also a fair argument that not shipping is the right call. A 30% heavier drive unit in a car sold on efficiency would be a bad product decision made for a good geopolitical reason. Holding the technology back until it's genuinely competitive is defensible engineering discipline, even though it looks like failure from the outside. The verdict is split, and it should be. The announcement was right, the timeline was fantasy. Both things are true at once. A Tesla isn't alone. A BYD builds its own motors and batteries, but building your own motor doesn't exempt you from where the magnet material comes from. Toyota has pursued magnets that reduce heavy rare earth content rather than eliminate it. And at least one startup is pursuing a motor that generates its magnetic field through software and power electronics rather than fixed magnets. The odds are long. The fact that it's being attempted tells you how valuable the answer would be. Here's why this matters even if you never plan to buy an electric vehicle. When a manufacturer announces a technology with no production date attached, treat the absence of a date as the actual news. Tesla's zero rare earth motor has gone 3 years without one. If you are comparing electric vehicles on efficiency, understand that motor design is now doing as much work as battery size. Two cars with identical pack sizes can differ meaningfully in real-world range because of what's happening inside the drive unit. And watch the supply chain news, because it reaches your driveway faster than you'd expect. The April 2025 export controls trimmed production at real factories within weeks. The rule underneath all of it: every efficiency gain has a supplier attached. The further you push efficiency, the more concentrated that supplier tends to be. The best material almost always comes from the fewest places. That's the trade the entire electric vehicle industry made without fully discussing it. And it's now the trade everyone is trying to unwind at once. Was Tesla's zero rare earth motor a genuine engineering goal that physics simply hasn't caught up with yet? Or was it a promise the company already knew it couldn't keep on any useful timeline? Drop your answer in the comments. Everyone gets read. If this video gave you something to think about, a like genuinely helps this channel reach more people. Subscribe if you want the next one before everyone else.